Welcome everybody. So having discussed the DNA replication, the we have discussed the prokaryotic DNA replication. Now we will go into eukaryotic DNA replication. There are no much differences between eukaryotic and prokaryotic uh, replication. The only major difference are the DNA polymerases and the way they act. So first we will discuss the main eukaryotic enzymes which help in DNA replication. So there are actually 5 enzymes which help in DNA replication. So these are all eukaryotic. Sorry, these are all prokaryotic enzymes. Now we will discuss eukaryotic enzymes. So there are DNA polymerase are named as alpha, beta, epsilon, gamma, and delta. This has RNA primase activity. Beta and epsilon, these both are important over here. These both have proofreading activity. See, here this in prokaryotes, DNA polymerase 1 and DNA polymerase 2, 3, everything has proofreading activity. But the difference in the proofreading activity is there is always 5 prime 3 prime activity, whereas DNA polymerase 1 also has 3 prime 5 prime proofreading activity. Here also only beta and epsilon have proofreading activity, and beta like the DNA polymerase 2 in the prokaryotes which help in repair of the DNA. Your eukaryotic DNA polymerase beta also have repair activity, and your DNA polymerase gamma, remember as gamma, mama mitochondria. This help in mitochondrial replication. Your epsilon helps in Okazaki fragment synthesis. Okazaki fragment. Where does this Okazaki fragment synthesis occurs in lagging strand? Next, your beta has a repair activity. Your epsilon has initiation of replication activity. So this is the basics. So once you will revise the DNA polymerases, alpha, beta, gamma, epsilon, and delta. Alpha is for DNA primase. See, primase primary, alpha prime, alpha is A primary. That's how you remember it. Beta has repair activity. Gamma is for mitochondria. Epsilon is for initiation. I, but we'll refer as initiation. And you have delta is for Okazaki fragment synthesis. Okay. Next we are moving on to DNA repair. DNA repair is obvious. DNA repair is an important topic. We will go in retrograde. First, we will discuss the single strand DNA repair, and then we will discuss the double strand DNA repair. Before moving into DNA repair, I want you to just explain the basic structure of DNA, how it undergoes damage. See, you have deoxyribose sugars which are attached to each other by phosphodiesterase bond. So this is your basic sugar linkages. To these are bases are attached: thymidine, adenine, cytosine, and guanosine. All these are attached over here. This is how the basic structure of our DNA looks like. So let's first we will read the single strand DNA. Nucleotide excision repair. Specific endonucleases removes oligonucleotides containing damaged bases. DNA polymerase and ligase fill and reseal the gap respectively. Repairs bulk helix distortion lesions. Example, pyrimidine dimers. Occurs in G1 phase of cell cycle. Defective leads to xeroderma pigmentosum. Inability to repair DNA pyrimidine dimers caused by UV exposure. Presence with dry skin, photosensitivity, and skin cancer. So we will discuss it. See, once you have UV light have a property of pyrimidine dimerization. So, if you have water pyrimidine CUT, your dish you have uridine. You have only cytosine and thymidine. So the cytosine and thymidine, if is let's say your DNA sequence contains 2 cytosines and 2 thymidines. Now, once the UV light exposure occurs, this undergo dimerization. So they both get linked to each other. This thymidines gets linked to each other, which forms dimers. So that's why we say UV light is harmful. How to repair this? Once you have pyrimidine, once you have UV exposure, you need to remove this segment of DNA and you need to replace it, because this thymidines have undergone uh, this thymidines have undergone dimerization. So you need to repair this. How do you repair this? We repair this by using endonuclease activity of DNA polymerases. So first you have UV exo endonuclease or exonucleases. They meant the same. They create the nick in the two sides of your DNA strand which is defective. Once they create the defective strand nicks, then you have DNA polymerase. Which DNA polymerase do you think act here? Yes, yeah, beta. Because we are repairing. We know repair is done by DNA polymerase beta. And we also have repair activity and also proofreading activity. Proofreading activity is only by beta and epsilon. These both act over here and and create the new segment. Once the new segment is created, you need to just glue it. How do you glue it? We use ligase. So the basic activity that is going on here is, once you have UV light exposure, you have dimerization of your pyramids. You need to remove these pyrimidine dimers. How do you remove these pyrimidine dimers? By using the endonucleases. Which are these endonucleases? These endonucleases are also called UV dependent endonuclease or exonuclease. Once you remove this exonuclease, once you remove the damaged segment of DNA, you have a gap over here. To fill the gap, we have DNA polymerase beta, DNA polymerase epsilon, which comes and which forms the new strands, and the DNA ligase which seals it by gluing the both ends. That's how your nucleotide excision repair happens. Now, if you have a defect in this repair mechanism, you have xeroderma pigmentosum. What do you mean by xeroderma pigmentosum? See, we will get exposure to UV exposure as usually when we go to sunlight. But since we have nucleotide excision repair mechanism, our DNA gets repaired it easily. If you have defective in this mechanism, your DNA doesn't get repaired. So it leads to skin cancers, photosensitivity, and dry skin. This will all happen, and it looks like a hypersensitivity to sunlight. This all process will occur in G1 phase of cell cycle. Okay. Yeah. Base excision repair. What do you mean by base excision repair? Base specific glycolysis removes the altered base and creates AP, apurinic or dipyrimidic sites. One or more nucleotides are removed by AP, which means apurinic or apyrimidic endonuclease, which cleaves 5' and apyrimidic or apurinic ligase cleaves 3' and DNA polymerase beta fills the gap and DNA ligase seals it. Occurs throughout cell cycle. Important in repair of spontaneous or toxic deamination. The mnemonic is gel phase. So what is the basic problem and how do we deal with it? See, this is the normal DNA. Sorry, this is abnormal DNA. You don't have uridine over here. So let's go to basics once. Uridine on methylation gives thymidine. On amination gives cytosine. Once this gets deaminated, you have again uridine over here. So you have or else you will not have any nucleotide over here, which creates a apurinic site or a pyrimidic site. What is apurinic site? When you don't have purine over here, it is called apurinic site. And when you don't have pyrimides, which are CUT, which is known as apyrimidic site. Once you have apurinic site or apyrimidic site, the apurinic or apyrimidic endonuclease act over here. See, endonuclease lies and removes the backbone segment. Oh, what is backbone segment? We already discussed. See, this is phosphodiesterases bonds, and these are your nucleotides attached over. Sorry, new bases, nitrogen bases are attached over here. This is N Phosphodiesterase bond. This is N beta N glycosidic linkage. This bond over here is very unstable. It can break very easily. So once you have a break over this bond, which is N glycosidic linkage, you have an apurinic site or apyrimidtic site. To see this apurinic site, apyrimidtic site, we have endonuclease activity. What do you mean by endonuclease activity? Your endonuclease activity is nothing but when we have a long segment of DNA, it creates a nick over here so that your DNA gets open. Once your apurinic site, aperiodic nickel endonuclease make a nick close to this side where the base has been lost. If there is a nick, this DNA gets exposed, right? And DNA polymerases can act over here. DNA polymerases. What are these DNA polymerases in eukaryote? We know epsilon and beta. Remember this beta, which is for proofreading and for repair. Once this beta and epsilon will start act over here, they'll remove a segment of DNA. See, in the nucleus, I have acted over here, and they created a nick over here, which allows your DNA polymerase to act. Once this DNA polymerase act, they'll use their endonuclease activity and remove some portion of DNA, and by proofreading, and they'll use their polymerase activity to make a new strand. See, so you have a new correct a nucleotide which has been replaced over here, and then the DNA ligase will act over here and they will seal this. So you have repaired your base excision repair. Now coming to mismatch repair. Mismatch nucleotides in a newly synthesized strand are removed and gap is filled and retailed. Occurs predominantly in S phase. This is important, S phase, whereas your G1 phase has nucleotide excision repair. See, G1 phase nucleotide excision repair, mismatch repair occur as phase. Defective leads to Lynch syndrome, which is HPCC, hereditary non-polar process colorectal cancer. What do you mean by mismatch repair? See, what do adenosine over here has? This is the correct amino acid, but you have G-guanosine, which is incorrectly placed over here. So to remove this sequence of to remove this nucleotide which has been placed in place of thymidine, we need to remove this segment of DNA. How do you remove this? See, before removing this, we need to analyze which is the correct segment of DNA. Is this the correct segment of DNA? Is this the correct segment of DNA? So to analyze which is the correct segment of DNA, we have methylation. What do this methylation do? If let's say in this segment of DNA, this is the correct strand, this is the improperly placed DNA, which is your wrongly misplaced. Let's say misplaced nucleotide. Once you have methylation of here, you have methyl. The correct strand gets methylated. This strand doesn't get methylated. So by this, your endonucleases understand, okay, this is the correct strand. So I need not to change any sequence over here. The sequence that I need to nick over here is the wrong strand, which is non-methylated strand. See, you have GATC endonuclease acting over here. This GA endonucleases scan the defective strand and make a nick at nearest GATC sequence. Let's say here you have GATC sequence. See, these endonucleases make a nick over here. Once they make a nick, as we see in base excision repair, you have DNA polymerases, all DNA polymerases, beta, epsilon, which act over here, and they create a new nucleotide sequence and the ligase which repairs it. So that is how your mismatch repair also happens. I'll try to summarize it. Wait a minute. Yeah. So this is your DNA. Your DNA has phosphodiesterase bonds. Your DNA is linked to nitrogen bases. These nitrogen bases are linked by and beta and glycosidic linkage. First we have discussed the single strand repair. In single strand repair, there can be three type of defects. One, there is no nucleotide placed in this sequence, which is known as base excision repair, and this is the most common repair. Or you have misplaced, which is mismatched DNA, or sorry, mismatched nucleotide placed over here, and or else you can have a dimerization, which is by UV light, which is known as nucleotide excision repair. This occurs due to UV light. So the main right, okay, in base excision repair, the main in process includes endonucleases. First action of endonuclease remove makes a nick over there, and you have DNA polymerases beta and epsilon, which creates a new segment, and then you have ligase which seals it. That's it. Simple. In mismatch repair, you have first methylation, which since you need to differentiate which is the true strand, which is the false strand, and then you have DNA. Sorry. Once you have methylation, you have GATC endonucleases, which creates a nick over here. Once they create the nick, then you have action of DNA polymerase with beta epsilon, and then you have action of ligase which seals it. That's it. We have a clarity. Once you have no nucleotide, this was base excision repair. Once the nucleotide has been misplaced, that is known as mismatched nucleotide. Once you have a dimerization due to UV light, this is known as nucleotide excision repair. In nucleotide excision repair, let's once discuss the steps and we'll summarize it. So you have helicase. What is helicase? See, you have a dimer. So to remove this segment of DNA, you need a helicase which break downs all these hydrogen bonds over here and opens up like this, like a replica. Let's compare it with the replication fork. Once this replication fork is created, then you have action of your UV specific endonucleases or XC nucleases, which removes this strand, and you have DNA polymerase beta and epsilon, and the same story again, and the reaction of ligase. The important thing you remember is helicase. Sorry, I have forgot over here. Let me add it over here. You have helicase action of helicases. So that's how your single strand repair has been done. Now you need to have a double strand repair. What is the difference between single strand repair and double strand repair? If you see a single strand repair, the basic um, repair that you must do is over the N-glycoside linkage, which has undergone breakage or it has been misplaced. Whereas in double strand DNA repair, there is a backbone. The backbone, which is your phosphodiesterases bond, those have broke over here, and which leads to your repair, which leads to breaks in your DNA. So once you have your phosphodiesterase bonds have been broken, first I'm telling the basics, then we will move forwards to all this that is given over here. Once you have break in phosphodiesterase bonds, what will happen is you can repair it by two mechanisms. One is non-homologous repair, other is homologous recombination. Okay, so that's the basic. Now we will go into non-homologous end joining and homologous recombination. In non-homologous end joining brings together two ends of DNA fragments to repair DNA, uh, to repair double strand breaks. Homology is not required. Part of DNA may be translocated, may be dysfunctional in the ataxia telangiectasia. So wait, I'll explain this theory. Just try to concentrate. Uh, wait. 1 minute. Yeah. Non-homologous repair. So for any homologous repair, first we need to understand how a DNA damage get occur over in double strand DNA. So to damage a DNA phosphodiesterase backbone, you need ionizing radiation. This ionizing radiation converts your H2O into H plus and OH minus. These are very toxic radicals that can destruct your phosphodiesterase backbone, which leads to your double strand damage. Okay. Now this damaged double strand can be repaired by two mechanisms: non-homologous mechanism and homologous end repair. First, we will dive into non-homologous repair. In non-homologous repair, you have ionizing radiation which has damaged your DNA. Now, the important point lies over here. You have your Fanconi anemia protein complex. This is all not given over here, but for our understanding, we are just diving some more deep into non-homologous and repair. So, this Fanconi's anemia protein complex will recruit ATM DNA helicase. This, KU helicase. KU helicase. This ATM is nothing but DNA dependent protein kinase. This ATM, which is ataxia telangiectasia protein, which phosphorylazes KU helix and P53. We know P53 is nothing but tumor suppressor gene. This tumor suppressor gene will stop cell cycle. Why it needs to stop cell cycle? Because there is a break over DNA, and only when there is a correct sequence of DNA, you need to replicate the DNA. Until then, you just stop the cycle by using P53 gene. This KU helicase will repair this break of DNA breaks. How do it repair? It repair by non-homologous recombination and joining. What do you mean by non-homologous and joining? See, this is DNA, and you have over here your KU helicase will attach over the both ends of your breaks. So once this attaches, you have your opening of DNA strands. See, this DNA strands will open. You have KU helix over here, and they will just join when there are the complementary bases to each other, which leads to let's say here and here. And this excess amount of DNA which is present over here, have you understand? Wait, I'll write again. See, you have open and over here. Until they find the complementary basis, they'll go on attaching, and this extra amount of DNA which is present over it is lost. So it is a very dangerous mechanism, because we are losing some amount of DNA, and so this is how your non-homologous end repair occur. Yeah. You break over here, and opening of your DNA strand by KU helicase, and they'll link over here. See, wait, I'll draw it with another color. Yeah. Okay. So now what will happen is, you have attached over here, and this extra amount of DNA which is present, see, this extra amount of DNA which is present, they get lost in non-homologous end joining. That's how your non-homologous end joining occurs, whereas your homologous recombination requires two homologous DNA duplicates. A strand from damaged dsDNA is repaired using complementary strand from intact homologous DNA. dsDNA is a template. Defective in breast ovarian cancers with BRCA1 or BRCA2 mutations, and in Fanconi's anemia restores duplex accurately without loss of nucleotides. So what they're trying to tell is, you have a break over here in your DNA sequence. Now we are going to repair it by using homologous recombination. So in a chromosome, let's say you have two pairs of each DNA copy. Let's say this here it is chromosome number 11 and you have a break over here and this is the correct sequence which is present. So this sequence will act complementary to this break DNA and will repair it. How do we do it? So first what will happen is your DNA polymerases, sorry DNA exonuclease will act over here and repair and remove this segment of DNA. So once this segment of DNA is removed, you have 3 prime, 3 prime, 5 prime, 3 prime, 3 prime. So what will happen is another copy of same chromosome will act as homologous DNA sequence which comes to break sites. Once they find a break site over here, you have DNA polymerases which try to create a overhang edge in the homologous DNA repair. Once you have DNA polymerase acting over here, they will create a overhanging edge. Then the same DNA polymerases will use exonuclease activity. Once this exonucleate activity is used, see, you have DNA break, you have a DNA polymerase act over here, which creates a overhanging edge, and then you have DNA exonuclease acting over here, and this strand of DNA which has broken up, see, it has come here and it uses complement this strand of DNA as a complementary DNA and synthesizes new strand of DNA. See, the repair has been. So that's how your homologous and repair occur. That's about your non-homologous and homologous and repair. And your nucleotide excision repair, phase excision repair, mismatch repair. Hope I was clear. So before going into the next topic, let me summarize some of the diseases or syndromes that has been linked to our DNA repair mechanisms. First, you have ataxia telangiectasia, Bloom syndrome, Fanconi's anemia, and breast and ovarian cancers. SCID. See, this ataxia telangiectasia, Bloom syndrome, SCID are all these linked to non-homologous end repair joining defects, whereas your breast and ovarian cancers are linked to homologous end joining repairs. Your Fanconi's anemia is also linked to homologous DNA repair. Your xeroderma pigmentosum is linked to nucleotide excision repair. Okay. SCID, ataxia telangiectasia, blooms, non-homologous end joining, Fanconi's anemia, breast cancer, or homologous end joining, xeroderma pigmentosa, nucleotide excision. That's it. Okay.